In this lecture, we want to talk about some introductory methods of solving differential equations, including graphical methods and Euler's method, which is an algorithm for solution. So the first thing to sort of look at, and the reason this is nice, we can do this with a first order differential equation because remember the first derivative represents slope of a curve. And so it enables us to visualize how differential equations might be solved. Um, Sometimes it's easier to visualize things when you're looking at an easy problem, and then you can extrapolate that to a more difficult problem which you can't visualize quite as easily. So we'll use this concept repeatedly throughout the course, and this is sort of the first example of how we might do that. So if we just look at a very basic differential equation, y prime is equal to y plus x, what this graphical method of directional fields does is it basically selects values of x and y, and from that gets values of y prime. So I have a little table over here that I put together in Excel where I just plug in values for x and y, and these are just some random values that I plugged in. So I plug in 0 and 0, which in my coordinate axis would be this position 0, 0. And of course, if I plug in 0 and 0, I get 0, and that represents the slope. So I could come to my 0, 0 point and put a little tiny arrow here representing 0 slope. And then I do a similar thing for 1 and 0, 2 and 0, 3 and 0, 1 and 1, and so on, basically filling in this table with different values. And then at each location where I've selected a value, I could basically plot the slope at that particular point. And so what I will find is basically I generate this plot at particular point locations of slopes. And so this is what's referred to as a direction field. And then once I have these slopes, I can find a starting point here and basically trace through a curve at a given location. So you can see we've just picked some various points and chosen to trace out curves. And these, of course, are your family of solutions that are generated for a given differential equation, in this case this one. And note that I could do this with any first order differential equation, even if I had a very complicated function of x and y, by just selecting values of x and values of y and locating that on the coordinate axis and plotting the solution that I get for y prime. So this allows for a very visual solution and a selection of family of curves that can be visualized graphically. So another technique is known as Euler's numerical method. This is an algorithm-based method where we basically have some ordinary differential equation, and we have an initial value. So we have a known x sub 0 and y sub 0. And what Euler's method does is it gives us an approximate solution for values at equidistant points away from x sub 0. So for example, if our starting point is x sub 0, then our next point would be x sub 0 plus h, where h refers to a step size. And our point after that would be x sub 0 plus 2h. So we're basically stepping through values of x with known step sizes. Now, most of you know enough at this point about algorithm development and computer programming to know that obviously the advantage of a small step size is we get a much better approximation because the step size is smaller. The disadvantage is, of course, computational time. So for a known x sub 0 and y sub 0, we can then calculate point y1 by taking y sub 0 and adding a step that in this case multiplies the f of x sub 0, y sub 0 value. So we're actually taking the previous, or we're taking the something kind of analogous to a slope. And h here is the step size. So here's an example of what Euler's method would look like. we start with our x sub 0, y sub 0 point. We come to our x1 point, and our actual y1 point that we calculate from Euler's method, which is this constant h times f of x sub 0, y sub 0, places us at this point where in fact the actual solution curve would lie somewhere up here. So you notice that there is some error then in solution. And now if our next starting point is at point x1, then that error could conceivably get magnified as we increase step size, or as we increase the number of steps. Notice that if our step size were very small, as our step size gets smaller and smaller, notice here that the error is less and less between the solution curve and the solution based on Euler's method. So it is an algorithm-based method. It does generate a set of solutions. The accuracy of the solutions is really dependent on the step size. A lot of times in practically based problems, you want a pretty clear boundary condition, and a lot of practically based problems will have kind of a recheck method where they come in and reset that error based on some known conditions throughout the problem. So the problem's kind of overspecified. That enables a little bit of a reduction of this accumulation of error issue. So if we think about analytical methods of solving differential equations, we've looked at graphical methods, which is almost like an experimentally based system and really only applies to the case where you have a differential equation that's first order. And then Euler's method, also kind of similar, first order. It's a computational approach. One is a graphical approximation, the other is an algorithm-based approximation. If we want a true solution, an analytical solution, then we actually have to have an analytical method to solve the differential equations. And the most fundamental of these when solving first order differential equations is separation of variable method. So in the separation of variable method, the goal is to get all the variables in y on one side of the equation and all the variables in x on the other side of the equation, and then to use integration on each side. So if we start this first line here, we've already done that. We've gotten all the variables of y over here on the left-hand side. So this is some function of y times y prime, and then this is a function of x on the right-hand side. And then remember, y prime can be written dy dx. And now we'll multiply both sides of the equation through by dx. So on the left-hand side we have g of y, some function of y, dy, and on the right-hand side we have f of x, some function of x, dx. And then we can integrate both sides. So when we integrate the left-hand side, we generate a function in y. When we integrate the right-hand side, we generate a function in x. And then we have some constant of integration that is added as a result of the integration. Sometimes equations are not always separable. Some equations are never separable. Some equations can be separated if we introduce a transformation. So a classic case is where we have variables we have differential equations that contain y over x and powers of y over x. And so in that case, if we have a lot of terms in y over x, what we might do is we might make a substitution that we let y over x equal u. And so multiplying through, this means that y is u of x and y prime is u prime of x plus u. So this is the chain rule applied. So I'm sorry, this is the product rule applied. So we take the derivative of the first times the second plus the first times the derivative of the second, and dx is just 1. So now we have a substitution that we can make for y and a substitution that we can make for y prime. So if y prime was some function of y over x, which in its natural state would be almost impossible, it would be impossible to separate, we can now make a substitution for y prime given this equation here that we derived. So y prime becomes u prime of x plus u. And we can make a substitution for f of y over x by substituting f of u. So basically, wherever we have a y over x, we substitute u. And wherever we have a y prime, we substitute u prime x plus u. And then we can do a little manipulation, moving the u over to the right-hand side. And as long as f of u minus u is not equal to 0, then we can generate the following equation. So this is the equation that we would ultimately use then to integrate both sides, and it becomes separable because we made this substitution. After the differential equation is solved, what you can then do is you can come in everywhere you have a u, and you can resubstitute y over x so that you get things back in terms of y over x instead of in terms of u if that's what you wish to do. So separation of variables is a classic technique, a classic analytical technique used to solve differential equations, and is really the first order approach when you're solving a first order ODE.